Hello and welcome to the new episode of the solid state physics. And here I'm going to talk about the same concept that we talked about in the last class, that is the Drude model. And we saw that how the conductivity of a material has been calculated by the Drude model. So what I would like to do is first we will cover a very short recap of what was Drude's model and why it is kind of very important. So one thing I want to make clear is that when we are studying these models, the equations and the maths, they are important, but also the sequence of the models and why they were motivated and what were the key assumptions and what are the key shortcomings and areas or room for improvement. These are the things that we need to be very careful about, because what in this whole lecture series, what I want to highlight is not the maths, because the maths will be like more or less available everywhere. But the thing I want to highlight, or maybe like shed a little bit more light on, is what is the sequence and what is the connection between the different concepts in solid state physics, because it's a very large field, and it's a very large, it has a lot of materials, and there are small areas or small subsections of it which seem to be disconnected at first, but when you realize and when you study it, then I want to highlight that there is a connection. And these models and these scientists that you are seeing, for example, Drude or Sommerfeld or Joule, that scientists I have talked about in the later or earlier episodes, sorry, we have to think them as like experimentalists who are experimenting with their thought process, or they are trying to see some experiment from which they are gathering some information, and based upon the common sense of those that time, contemporary common sense about different things, they will propose a model to their best of understandings. So they are also trying their best to come up with new theories of reality. So, for example, we talked about how heat and electricity were gases or fluids, they were thought to be fluids, and taking that into mind, the like contemporary theories were made, right? So, similarly, we have to like sometimes what happens is when you see a model and it has a lot of like flaws, it has a lot of shortcomings, so better models have come to make the like study of the subject better. So the models which were in the beginning, they might look a little bit stupid, but that's not true, because that was kind of the best effort of that person to get around or like to discover the issue. So today's model was you know, it was motivated in an era where electricity and heat were thought to be were thought to be different. So let me use a different ink. Different fluids different fluids invisible fluids alongside the atoms making up the molecules. That is what it was thought to be. But what was Drude's model? Drude's model, the genius of Drude's model, the genius of Drude's model was unification of unification of heat and electricity under a single banner, under a single theory rather. It's a single banner, but it's like a single theory. So it's a single theory, and people were already seeing from experiments that heat and electricity, the conduction of heat and the conduction of electricity, they are kind of related, right? So when the thing was like electricity and heat, they are being studied more, it was already discovered that heat is not some fluid, but it's energy, or it's the kinetic energy, and electricity was also shown to be motion of such certain particles. So it was kind of thought, okay, they might have some connections. So Drude's model was the grand unification of heat and electricity. And the other thing will be, what will be the basic assumptions? Electron, this is like the one line in basic assumption. Electrons are ideal gas particles, seldomly colliding with nuclei elastically, or almost elastically, almost. So basically this is the assumption of Rude's model, and by this simple assumption he could unify the electricity and heat. And that's pretty awesome. That's actually, because I mean, given the time frame, given that there was literally no theory about heat and electricity, this theory was pretty good. But later on, people started to see that, oh, it does not quite predict certain properties. It predicts the values larger or smaller, and we will see that. But this class we are going to focus on how does Drude's model talk about heat transport. So we talked about conductivity, we talked about electricity transport, but here we are going to talk about heat transport. So heat transport is done by electrons as thought by Drude's model, but that was later proved to be wrong, because like not only electrons but also the charge centers itself themselves, they actually carry heat with them. So this will be a shorter class, because this will be kind of only explaining the heat conduction, right? So the heat conduction. So heat conduction is generally dictated by a certain formula, and it's like it's called Fourier's law. There is a Fourier transformation, but it's not that. It's Fourier's law. And what's Fourier's law? It says that Fourier's law states that the heat current, or like the amount of heat passing through by each unit time, is given as J grad T. So I will explain what is that, but it's it doesn't need a very mathematical description at this point, but it's basically the temperature difference. You can think of it in simple terms as temperature difference. So this is jq equals to minus j grad t. This is a coefficient. Often, actually, this coefficient is sometimes written as lambda. I will write it as lambda. So lambda is the coefficient that we are talking about. So lambda is also called the heat conductivity um, of the system. Now the thing is, from a rigorous analysis, we can say that um, lambda is the heat conductivity, right? Heat conductivity. Lambda is given as what? Lambda is often given as 1 by 3 L V C. So what is this formula? This, it has some terms which look familiar, but I will explain what is these. What are these? Um, so okay, this is the average root mean square velocity. Root mean square velocity of electrons. Okay, this is the root mean square velocity of electrons. Um, so it's often given as 3 kbt by m. or maybe not this. Okay, so let me just this is given as 3 kbt by 2, so v is often given as under root 3 kbt by m. So this is the root mean square velocity of an electron, and it's kind of the measure of the average kinetic energy. What it does, it gives you an idea about the average kinetic energy, and m is the m of electron, so you can think of it as m of electron. So how do we get this value? We get this value from the Maxwell-Boltzmann distribution that we discussed earlier. Okay. Um, right. So L is the mean free path, and CE is the heat capacity. And CE is also will be given as a function of t. So it's not a function of t, but it's rather given as 3 kb by 2 into Ne. Ne is the number of electrons per unit volume. So how do we get that? We also get that actually these V and this C is um, they are interrelated. So as we can see that the total kinetic energy half mv square in a unit volume will be given as this. So this is kind of, you can see this, if we call this U, then this will be um, 3 by 2 kbt, right? So CE is defined as du dt. So what is the heat capacity? Heat capacity means but per unit temperature what is the increase in energy. So that will be given as 3 by 2 kb Ne. Okay. So now we have everything with us. So lambda is given as 1 by 3 L V C, and L is mean free path is given as V into tau, right? So from a very simple analysis, that if there are two particles, two ion centers, ion, and there is an electron which is going from here to here, and like it takes around tau time, and it has a mean square root root mean square velocity of v bar, then the length will be obviously given as v bar into tau. So saying that, what we have is tau v bar square ce. So this is given as 3 kbt by me, and 3 kb into 3 by 2 kb into Ne. Okay, so if we simplify this, what we will get is 3 by 2 kb t square tau, sorry, not t square, kb square t tau by me. So that is what we are going to get. So let me scroll down a little bit. Okay, so yes, I think now it's visible. So this is the formula for the lambda. So now we can see that, so yeah, we write it 3 by 2 tau kb square t by me, and sigma, if you remember from the earlier class, it was given as Ne e square tau by me. Okay, so what we will see is if we divide these two things, then we will see something very interesting. So if we divide lambda divided by sigma, lambda divided by sigma, then what we will get, tau will cancel, we will the kb square will be there, kb square, there will be 3 by 2 obviously, there will be a t, tau will cancel, me will cancel, and Ne will also, okay, there is an Ne, sorry, Ne will also cancel. So there will be an e square, right. So this will be the, let me write the temperature in nearby, and and that gives us this equation, which is this. We can see that the lambda by E, the heat conductivity divided by the electrical conductivity, it is proportional to temperature. So we can, and this constant L, this is often called Lorenz constant. This is independent of any material properties. So that is very interesting, because we can see Kb is Boltzmann constant, it's a fundamental constant. E is electronic charge. So this L thing, this L quantity, it's basically a constant which is independent of the um, geometry or specific properties of the material, right? So it doesn't depend on what kind of material it is, how many electron it has, how many valence electron it has. It doesn't depend on anything of that. So, and if you calculate the value of L, it comes out to be 1.11 into 10 to the power minus 8 volt square k to the power minus 2 Kelvin or volt square divided by Kelvin square. And for, so why it's so remarkable, it kinds of, not kind of, but it definitely tells us that there is a clear cut um, connection between the electric conductivity and the heat conductivity, and there is a well defined formula for the ratio which is also dependent on temperature. So this L is irrespective of any L is constant irrespective of any material, is called, it's a famous law, it's called um, Wiedemann-Franz law. And this T dependence is also very well documented, and um, yeah. So there are two takeaways. One is lambda by E is proportional to T. There was an experiment by, sorry, not Joule, but Lorenz, which found that yes, it is indeed the case. And the second takeaway is this L is independent of material properties. So, actually, if someone takes a measurement for most of the materials, the L value will be between 2 to 3 into 10 to the power minus 8 volt square per coulomb, Kelvin square. And the interesting fact is, Drude actually mistakenly, he took some different assumption that we did not take here, and he got the double of the value that we got here. So he got a value of like um, L equals to 2.22 into 10 to the power minus 8. This is what we got from the theory, and this is the experiment. So as we can see that it's very strikingly similar, and this was cited as one of the best reasons for Drude's model to be correct. So this tells us that Drude's model is correct. Seems to be correct. Seems to be extremely correct, extraordinarily correct. Good. But what happens is that Drude's model is bad. Drude's model, when it comes to Drude's model, the mean free path, it gives bad predictions. When it's let's say the sigma, it gives bad predictions. And so these are kind of the things, it gives bad predictions, but like it also gives bad predictions for this. So but when you take all of this into account and you calculate this quantity, then the errors that you had in the theory, they cancel out. So it gives a correct result. So that was later found out that this correct result is just a coincidence of the individual errors cancelling out, and this Wiedemann-Franz law, it's also not applicable when the temperature drops to near zero. So that is something that we will see. So in this class, that was pretty much it that I wanted to talk about. In this class, we saw that how Drude's model is also very effective, and also it gives an effective description of how heat is transported, and it gives an effective description of a thing called lambda, which is the heat conductivity. And from the kinetic theory of gas and like some other more involved analysis, we can see that lambda is given by this, and from this formula we could arrive at the Wiedemann-Franz law, and also we could see that it is very in a very good agreement, in extraordinarily good agreement with experiment, and but that was an error, that was a coincidence which was caused by the cancellation of errors in the individual quantities. So that means Drude model is, I mean, it's a good starting point, but it's not really correct. So in the next class, we will in detail go into that, um, why Drude model is still used in some places, where they are used, and what are the compelling shortcomings of Drude model. And we will see that how they are experimentally verified. And we will see that how the next model that we are going to talk about, that is nothing but the Sommerfeld model, that is the quantum model. The Drude model was classical, Sommerfeld model is quantum. So we will see that why Sommerfeld model was motivated, why it was necessary. Just like all of the theories that we are going to talk about, we will see why they are necessary and why they are motivated in that time in the contemporary like scientific community, why they were needed. We will see that, and then we will go forward and we will study the Sommerfeld model in full detail in later classes. So see you in the next class. Best of luck. Thank you.